Reactions of carboxylic acids. We'll look at 6 reactions. Each one of these has a lot of practical applications for body chemistry. Here's a 2-carbon carboxylic acid. Its common name is acetic acid, or its IUPAC name would be ethanoic acid. Here's the hydrogen that's acidic, and this is the active ingredient in vinegar. And vinegar has a little bit of zing to it, you know, when you taste it, and that's true of acids in general. They're a little bit sour. So if you taste something with a little bit of zing, chances are it's got some acid present. And an acid, as you know, can donate its proton. So if we have acetic acid and water, the water is going to pick up the proton. We get an ion then, it's called the carboxylate ion, NH3O+ as the product. Simply dissolving an acid in water gives us that particular reaction. Because carboxylic acids are acidic, then that means that they can react with bases. And here again, I've tried to color code so that we can get a feeling for what happens in the reaction. This proton of the carboxylic acid is going to react with the polyatomic ion OH- to give us water, and the other product will be a salt, an ionic compound of the carboxylic acid. Sodium acetate would be its common name, sodium ethanoate, its IUPAC name. Here's another example of that reaction. This time I've got a benzene ring with a carboxylic acid group attached. Instead of using the base NaOH, I've got KOH. So we'll get the potassium salt. This is potassium benzoate. And potassium benzoate is the active preservative in foods like ketchup. Let's look at another example of this reaction. Here's a long chain carboxylic acid that we'll encounter in biochemistry. It's called stearic acid. That's its common name. And the parentheses with the 16 after it, well, that indicates a long chain. In other words, we'd have 16 CH2, CH2, and so on. As it reacts with sodium hydroxide, we'll get the sodium salt of the carboxylic acid. So its name would be sodium stearate, which I misspelled, by the way. Sodium stearate, STEARATE. And salts of long-chain carboxylic acids are soaps. And so lots of those are manufactured. The third reaction that we'll look at is ester formation. We talked a little bit about esters when we looked at their nomenclature. Lots of esters in biochemistry. Fats and oils, for example, are esters. In this particular reaction, a carboxylic acid reacts with an alcohol. And again, using some color-coded chemistry, a molecule of water is going to be split out. It's a reversible reaction. Over the arrow, I've got acid and heat. Acids like to dehydrate things. And so as it pulls the water out, a water molecule from between these two structures, a bond is formed, giving us an ester. C double bond O with an OR, or an O carbon, is our functional group for an ester. And here's another example of that. I've got the same carboxylic acid, this time a 2-carbon alcohol. So we'll get a 2-carbon over here in the OR group, O-ethyl, instead of O-methyl up above. And I picked this particular one just so that I could mention, again, the common name for this material is ethyl acetate. You're not required to know common names. Its IUPAC name, though, we'd like you to be familiar with. It would be ethyl, and then a 2-carbon carboxylic acid ethanoate, ethyl ethanoate. And this particular material is the active component in fingernail polish remover. Our next reaction, number 4, Ester Hydrolysis. And hydrolysis means the reaction with water. It's the most common reaction in digestion, and the body can digest esters. So for example, when we take into our body fats and oils, these are broken down by the body in just the reverse of ester formation. So here I've got an ester. It's reacting with water, reversible conditions, and we get back the carboxylic acid and alcohol that form the structure. Let's look at another example of that. Here I've chosen an ester that's a little more complex in its structure. It's actually got 2 or 3 functional groups. It's got the benzene ring, it's got a carboxylic acid right here, and then up here is the ester portion. It's got a C double bond O with an OR. That makes it an ester. It's called acetyl salicylic acid, and you know that as aspirin. Here's what happens to aspirin when you take it into your body. Reacts with water. This ester linkage is going to be broken. We'll get back the alcohol and the carboxylic acid. So here's the alcohol portion up here. Over here's the carboxylic acid. And we get these 2 molecules. This is called salicylic acid, and it's the actual fever reducer in the body. Originally it was isolated from willow. They noted that willow bark had these fever reducing properties, and eventually they isolated salicylic acid and used it for a number of years. But because of its acidity, they tried to come up with something that wasn't quite so harmful to the esophagus and the lining of the throat, and Bayer came up with this idea for aspirin. Our 5th reaction is called Ester Saponification, and it too is breaking the ester apart. Rather than using water, it's using basic conditions, and in this case, because a base is used, rather than getting the carboxylic acid and the alcohol, we're going to get the salt of the carboxylic acid and the alcohol. So the O-ethyl will form ethyl alcohol. This portion would form the carboxylic acid salt. Let's look at our 6th reaction. We've included this 6th reaction, phosphate ester formation, because of this word ester. Here's the structure of phosphoric acid, showing the covalent bonds, and it reminds you a little bit of a carboxylic acid. Rather than a C double bond O, it's got the P double bond O with an OH. And phosphoric acid can react with alcohols in a manner similar to that of carboxylic acids. Using our color-coded chemistry, a water molecule is going to be eliminated from these 2 structures, and then we'll have the R group now attached to the phosphate. This is called a phosphate ester. And the reason that we've introduced phosphate esters in this chapter is that it lays the formation or foundation for our discussion of DNA and RNA in biochemistry. And both of these complex structures are examples of phosphate esters.